готовится.
Презентацию видно? Открылась?
Открылось, по-моему, все нормально. Паша, записывается там?
Ну, вроде да, должно.
Все. Все. Ну что, мы уже можем... Давайте еще пару минут подождем. Ведь вы в курсе, что у нас официальный язык английский, да?
Конечно, да.
Ну, хорошо. Окей.
Добрый вечер.
Привет.
Добрый вечер.
Привет.
Привет.
Привет, привет.
Pete, I think you can start now. So.
Okay, thanks. So yeah, so first of all, I would like to thank the organizers of the seminar for the opportunity to speak here. It's a pleasure to do it. So my talk is devoted to the so-called topological recursion for generalized weighted double Hurwitz numbers. I will explain in a moment who they are. This is all based on joint work with Boris Bычkov, Maxim Kazaryan, and Sergei Shadrin. The first part of this work is already on archive. You can see the number over there. And the second part, we are, still writing it down, but it should appear there soon as well. Yeah, I'm sorry. So this is kind of a large subject, so I won't be able to give all the details in one talk. I will present just the rough outlines. Then, yeah, maybe, well, okay, so just all the details will not, it won't be possible to fit it in just one talk. Let's start. So who are these general weighted Hurwitz numbers? Well, basically consider formal power series psi and y, like here, and consider a partition function of the form written here, where S lambda are the Schur functions written in p variables, the power sums. And here, so you can see that we have S lambda of p and S lambda of S over h bar. So we consider this partition function z as a function of p variables, while S, so these S guys, they are parameters. They are fixed in this formal power series y. So this is actually a kp tau function. This partition function turns out to be a kp tau function, well, which is quite natural, seeing as it's made out of Schur functions. And this is actually not, a specific form of specific class of kp tau functions, which are called kp tau functions of hypergeometric type. They were, for instance, studied in paper by Harchov, Marshakov, Mironov, Morozov from 95, and some other papers from that period, and also by Orlov and Sherbin in 2001, and in some of their following papers. Now, so who are the general formal weighted double Hurwitz numbers? They are these guys. Consider the logarithm of this partition function z, and consider the.
I'm sorry.
Yes.
May I ask a question?
Yes.
So this function y of z, it does not show up in the function z capital.
The function y itself does not show up, but its coefficients, who are sk, they do show up in the argument of the second sure function. I'm sorry, it's a bit confusing that I use sk as numbers, the formal coefficients in the formal power series y, and also I use s lambda for a completely different thing, the sure function. So you see we have a product of two sure functions, s lambda of p and s lambda of s over h bar. S lambda, it depends on actually p1 and so on, pk, where k is size of lambda variables, and when I write s lambda of s over h bar, I mean that I plug into the sure function variables number s1 divided by h bar as the first argument, s2 divided by h bar the second argument, and so on.
Okay, thank you. And one more question. The constants ck and sk, are they related somehow?
No, so they are completely, at this point, psi and y are completely general formal power series without any requirements.
Okay, thank you.
Yeah.
Sorry, Pete, just to continue Zhenya's confusion. So
Yes.
y, which is argument of psi, has nothing to do with the y function.
Sorry,
You
y,
have psi,
yes.
psi is a function of y.
Ah, yeah. Well, yes. Sorry, this is again a little bit confusing, but yeah, maybe. Well, in fact, you will see in what follows that this makes sense. This notation makes sense, but at this point, it's probably a bit confusing. Yes, psi is as an argument of y. At this point, it has nothing to do with y function. This is just a formal variable. So psi is a formal power series in formal y variable, and y is y of z is a formal power series in the formal z variable. So at this point, they are not related at all. Actually, in what follows, we will plug y into psi. So there is a reason for why we use.
I see.
So
then these p are usual kp's. Yeah, usually called T, maybe in some different normalization.
Yes, so they're related to the usual T's by pk is equal to tk over k, something like that, yes.
I see. And these S, which are sort of second hierarchy of times, like into the hierarchy,
precisely,
we
yes.
just put them to
we just put them as constants, so as parameters, yes.
So H bar probably means that you have some H bar expansion.
Precisely. So we will see this a bit later. Yes.
The properties of this expansion presumably depend on particular values of these S variables, which are fixed parameters.
In a sense, we can actually make some statements without any restrictions on the S parameters. So you'll see. I will give a precise theorem about that.
Okay, thank you.
Mm-hmm. So yeah, in fact, it turns out that this logarithm of z. So if you look at f here, it admits a genus expansion in a way like that. So this the second line from the bottom, it turns out to make sense, which is not, if you deal with formal power series, it's non-trivial. Why this line, second line from the bottom in this slide, why does it make sense at all? So why you can write it like that? But from what follows, you'll see that it does make sense. So we prove that it does make sense. So I'm a bit jumping ahead here. But so after we prove that the genus expansion does indeed make sense for this problem, for logarithm of z, we can define general formal weighted double Hurwitz numbers as follows. So as so this H, G, mu, where mu again is a Young diagram. So, sorry, so I should have commented that in Z here the sum is taken over all lambdas, where lambdas are Young diagrams, including the empty one. So we include so this sum is over all Young diagrams of all sizes, including the empty Young diagram. I'm sorry. So do you see my mouse pointer or not? So
yes, we do.
Okay. Yeah. Okay. Great. So yeah. So this line, it turns out. So you will see later that this line, second line from the bottom, it does make sense, and we define general formal weighted double Hurwitz numbers like this. I will, in a moment, I will comment why, how is this related to the original Hurwitz problem, which was studied by Hurwitz in the 19th century. Why do we even call those coefficients of some formal series as general Hurwitz numbers? It will be clear a bit later. So are there any questions on this definition of the partition function and the formal Hurwitz numbers?
So one question, is the case n equals 1 okay?
N equals 1. You mean here in the last two lines?
Yes, yes. Mm-hmm.
N equals 1 is okay, yes.
But then you have negative powers of h bar. Is it okay?
In fact, it's okay. So we will see that this makes sense. Yes. You see that we also do have some negative powers in Z. As in S lambda, you plug S over H bar. So Z itself does contain lots of negative powers of H bar. So in the logarithm, there will be a little bit of them. But yeah, this is okay. So are there any further questions regarding this definition?
Can this partition function be written in a convenient way using free fermions?
Yes, it can be written in a convenient way using free fermions or in bosonic. So you can, that is what we actually do in, not precisely. So it turns out that for this problem, more convenient option is to to proceed using the bosonic formalism, but it can also be written in free fermions. I think I should have some formula for it later in the free fermion approach, if I haven't forgotten to put it into the slides. If I have forgotten, then I can write it down a little bit later using just on the whiteboard. Okay, yeah. Well, let me say a few words on how this is related to known Hurwitz numbers and how it generalizes them. So you can see this table here, and here in this table there are listed quite a few of Hurwitz-type problems and how they are related to this partition function. It turns out that if you want, for instance, what's called simple Hurwitz numbers, so the original Hurwitz numbers which were studied by Hurwitz, I will actually, to illustrate the combinatorial meaning, I will give precise definition for them a little bit later. But let me say right now that simple, the usual simple Hurwitz numbers correspond to taking usual and simple in those two tables, where you take psi of y just equal to y and y of z just equal to z. So the simplest possible case, in fact, already corresponds to a non-trivial problem, namely the original Hurwitz problem. Now there are lots of generalizations of the original Hurwitz problem. So for instance, you can take what's called orbifold Hurwitz numbers. They correspond to taking z to the power some power q, which is not necessarily 1, but some maybe some integer larger than 1 in place of y, and keep psi equal to y. Then, well, you can consider, for instance, monotone, what's called monotone Hurwitz numbers, where you put in place of log psi, in place of so psi will be a log of this expression 1 over 1 minus y. There are also what's called strictly monotone Hurwitz numbers given by this thing in this formalism. There are what's called the hypermaps counting problem, which is governed by psi equal to log of this quadratic expression. You can consider Bousquet-Mélou Schaeffer numbers, which are governed in this case by.
Sorry, Pete. Can you send the file of your presentation?
Oh, sure. Yes, of course. Just one moment. Sorry, one moment. Okay, here is chat, and then send file in just one moment. I think it's this one. Yes. Right, so is everything okay? Does everyone see the presentation again?
So, with this, comparing these two pages, so you say that this function, which is y, so these s parameters, in some cases, there is a single s parameters and all others simply.
In some interesting cases, yes. In some interesting cases, you just take a single one of those as non-zero and all the others vanishing. But there are known interesting cases. For instance, look at the bottom line. What is this thing? Here I wrote it's extended Ooguri-Vafa, meaning that it's what's called the extended Ooguri-Vafa partition function of colored HOMFLY polynomials of torus knots. So this is a known thing, studied quite extensively. So you can, if you consider some knot, you can take all the colored HOMFLY polynomials and arrange them into a partition function, which is called the Ooguri-Vafa partition function. And if you take a PQ torus knot, so PQ here are just integers which parameterize the family of torus knots, then this Ooguri-Vafa partition function, it turns out to be of this Hurwitz form. And it corresponds to this infinite y, like here. But it also depends on an h bar.
Okay, I'm sorry, just to clarify, yes. In your table, so you take usual Hurwitz numbers, and this is psi, which is equal to y, right?
Yes, yes, precisely, yes.
or for monotone, this is psi, which is equal to 1 over 1 minus y. So
no, it's a psi equal to log of 1 over 1 minus y.
Okay.
So like as written. So.
Thank you.
So for usual, it's psi equal to y, and for monotone, it's psi equal to log of 1 over 1 minus y. So in this table for brevity, I've listed exponentials of psi. Yeah, so here, well, let me say a few words about the second part of the table. This is, so I wrote here that it's the age-deformed case. And in fact, you can consider, so let's go back a little, consider this in this formal series psi and y, you can consider the coefficients ck and sk to be some formal power series in h bar themselves. Actually in h bar squared. So you can consider ck and sk to be formal power series in positive powers, well, in non-negative powers of h bar squared, and then everything which I'm saying below, it makes sense. I will comment on that further as well. But if you consider the numbers which I wrote here, then actually you don't need this. You don't need the dependence on h bar. But in some interesting examples, including in the last line, this Ooguri-Vafa partition function of college HOMFLY polynomials of torus knots, your y will depend on h bar. So here, this capital A is the in a HOMFLY polynomial depends on two variables, q and a. So this a is precisely this a, formal variable entering the HOMFLY polynomials, and q is equal to x of h bar, your q from HOMFLY polynomials. Let me also comment on the first line in this age-deformed case table. This is what's called the case of R spin q orbifold Hurwitz numbers. This is a very interesting case. I will, if there will be time at the end of the talk, spend a little more time on that specific case. Why is it interesting? It's because let's go back to the usual simple Hurwitz numbers, those guys. So where y is equal to z and psi is equal to y. For those usual simple Hurwitz numbers, there is a very important celebrated formula, which is called the LSV formula, the Alexandrov-Chapuy-Eynard-Harnad formula, which relates them to the intersection numbers on the moduli space of algebraic curves. And the original ELSV proof of this was quite a complicated geometrical proof. Well, using, for instance, our technique, we can, in basically combinatorial way, reproduce this proof for usual simple Hurwitz numbers, the LSV formula. But also, if you look at the R spin case, there exists what's called Zvonkin's conjecture due to Dima Zvonkin, which was unresolved for something like 13 years or 14 years, 13, I think, years, or maybe 12 years, something like that. So he posed it, as far as I remember, in something like 2006. And so we proved it in 2019, I think, in a different way, actually, than the way presented here. But this is, in geometric way, it's so nobody could prove it. So the LSV type formula for the R spin Hurwitz numbers, which relate the R spin Hurwitz numbers to integrals of Kyoto classes over moduli space of curves. So if I have time at the end, I will talk about this a little bit more, because this was a long-standing conjecture which our techniques, in fact, allow to prove. Now, yeah, let me remind the definition of just the usual simple Hurwitz numbers to give a flavor of combinatorics to the talk. So to give an example where we have, I mean, all those problems actually they are well posed combinatorial problems, but I mean I won't obviously have time to present all those problems in detail, but let me do at least one of them, the simplest one. So who are these usual simple Hurwitz numbers which you obtain from this partition function? Well, in a way like that, if you put the simplest case psi equal to y and y equal to z, you obtain those h, g, mu. So who are they? What is the combinatorial meaning? Let me explain this. Consider some integer partition, and let's look at the symmetric group as D, where D is the size of this integer partition, and consider f factorization, tau 1 times and so on tau mu to tau m equals to sigma. So here we fixed a non-negative integer g, which will be precisely this g from h g mu. So this m is a number which you obtain in this way from g and mu. Here taus are transpositions belonging to the symmetric group SD, and sigma is a permutation of cyclic type mu. Now let's also pose the condition that the subgroup generated by all the tau i's, it should act transitively on 1 and so on t. Then let's count all these factorizations. So how many in the symmetric group as D, in how many ways you can represent a permutation of cyclic type mu as a product of m is fixed. Well, so if you have mu and g fixed, then m is fixed. So in how many ways you can represent inside the symmetric group as D a permutation of cyclic type mu as a product of m transpositions. So this is a well-posed combinatorial problem. And it turns out that, well, let's call the number of these factorization divided by, well, times some combinatorial factor. Let's call it this circle shouldn't be there. Well, for this definition to coincide with what I wrote earlier. So this is just what's called the connected simple Hurwitz number h g mu. So disregard this circle. Let me say a few words. So this is a combinatorial way to define these numbers, but there is also a geometric way. You can consider coverings of a sphere by genus G surfaces, and you can count ramified coverings where I don't know, let me maybe draw something. Just I will probably okay. Oops, one moment. Let me draw it here. So consider sphere, and then consider some genus G surface, and suppose you have a ramified covering of the sphere by a genus G surface, which looks like that. So here I'll draw it like that again. So here is infinity, and over infinity your ramification looks like that. Mu1, mu2, and so on, mu_n. So over infinity, this covering is ramified like this. And you also have some points P1, so on Pm, where M is this M, over which you have simple ramification with just only two sheets intersecting and no other ramification points. Then you can count up to natural equivalence. You can count such ramified coverings, and this precisely corresponds to this combinatorial problem. Originally, Hurwitz, I think he considered the geometric picture here. Yeah, so this is the reminder of who are the simple Hurwitz numbers. And well, I won't explain in detail why specifically you get precisely these numbers if you look at partition function like that with psi equal to y and y equal to z. So I won't explain it in detail right now. Oh, I'm sorry. So this, I think I will erase now the picture.
There is a button which erases old.
Sorry?
You can erase everything.
Yeah, I don't see it. Okay, I'll do it like this. Okay, yeah. All right. So let's go further. Well, in fact, if you want to just compute Hurwitz numbers, it's completely possible to compute them. So let's again go back to the first slide. So if you start with this partition function and then you want to compute the Hurwitz numbers defined like that, well, you can even put this in Mathematica, for instance, and it's rather effective. So well, you can effectively compute them straight from the definition, just from the partition function for any given psi and y, up to any order you want. So what are we interested in fact, in all this story, in this whole story? We are interested in what's called the endpoint functions. Let me define the endpoint functions. So the endpoint functions are generating functions of these Hurwitz numbers, which are defined like this. So you can define what's called disconnected endpoint functions if you take the original partition function z and just put it like that. Take the sum overall case. Here, capital X is for now a formal variable again. So this H disconnected, it's a formal series. So the original partition function is a formal series in P, in variables P, and the endpoint function Hn disconnected, which will be denoted with this filled in dot, or let's say bullet. So it's a formal power series in variables X. And we define these guys for every n starting from 1 and to infinity. And the connected endpoint functions are defined like that, where you take the logarithm of z instead of z here. Well, obviously, these guys are related via the usual inclusion-exclusion formula. And then if you consider the connected endpoint function, it admits genus expansion. Again, like I said, it's a non-trivial result, so this is related to Zhenia's question. A priori, it's if you consider just formal power series as in the definition, you don't know whether it's actually a valid expansion like that. whether these HGN, whether they will be, there are some formulas via some finite sums from the original expressions. But in fact, it turns out that it is valid. It follows from our theorem, which I'll give a little later. And then you can further expand this HGN in terms of X, and here the coefficients will be precisely the Hurwitz numbers. In fact, the general Hurwitz numbers. General formal weighted double Hurwitz numbers. Okay, so are there any questions about the definition of the endpoint functions? All right, so again, like I said, so we introduce those endpoint functions not because they allow to compute the numbers themselves in some easier way. It's already straightforward to do this from the definition, but it turns out that these endpoint functions, they possess some interesting properties. Namely, at this point, so from the definition of endpoint functions, you see that there are some not very complicated, but rather complicated infinite formal power series in X bar. And our first main result is that after a particular change of variables, you can, these HGN, they become finite expressions in a very particular sense. So I will, in a moment, formulate the precise theorem. So what is this change of variables? So the change of variables is this boxed one. So this is, again, if your psi and y, if they are just any formal power series, then this will be some formal power series, again, in Z. And here you can already see why, why I had this very confusing notation in the first slide, because we usually will plug y of Z in psi. So this, in a sense, makes sense. So what is this? What is this change of variables? This change of variables, in fact, it originated from the papers by Alexandrov-Chapuy-Eynard-Harnad. And there they, so what did they do there? They considered topological recursion. So I haven't said anything about topological recursion up to this point. I will introduce it a bit later. Just here I will mention the results of Alexandrov-Chapuy-Eynard-Harnad. So what they did was basically they considered, let's go back to the table. They considered, what did they consider? Well, they considered this second line from the bottom in the first table, polynomial weighted Hurwitz numbers, actually double, where this again is finite. So they considered arbitrary polynomials x of psi and y to be arbitrary polynomials. So this, for instance, it includes those three cases as well, but not these ones, straightforwardly. So they consider just the polynomial expressions for x of psi and for y, and they proved in a rather complicated way, using some techniques coming from matrix models and so on. So they proved this so-called topological recursion, which I haven't defined up until now, for these polynomially weighted double Hurwitz numbers on the spectral curve given by this expression. Again, I haven't yet defined what is.
Sorry,
Yes.
but I'm a bit confused. When you say change of variables, what you change for what?
Yes, I will say it in a moment. So in Alexandrov, yeah.
Does this x of z has any relation to this axis? You have just introduced.
Yes, precisely. So it does. It does. So I will say it in a moment. What will be the change of variable?
So when you say change, so that can be interpreted as some spectral curve, though.
Well, yeah, it's
a formal spectral curve, if you wish. But okay, could you make it more precise?
Yeah. That's what I was going to do just right away. So that's precisely what I wanted to say right now. Again, at this point, so let's consider this formula in two ways. So one way is how originally it was considered by Alexandrov-Chapuy-Eynard-Harnad. So they consider it's not a sound change of variables. They consider it as a spectral curve. So they consider some CP1, a curve CP1 with global coordinate z, and they considered functions y of z and x of z given by this formula in terms of so where y and psi were polynomial expressions. So this gives them a spectral curve. So this boxed formula in terms of Alexandrov-Chapuy-Eynard-Harnad, it's a spectral curve. On it, they run topological recursion, which I will define a bit later. And it gives them, it reproduces, they proved that it reproduces the endpoint functions for this specific problem. Now, let me explain why now I say that we can treat it as a change of variables at this point. Let's consider now our problem, not Alexandrov-Chapuy-Eynard-Harnad's one where they had polynomial expressions and a well-defined spectral curve. Consider arbitrary formal power series psi and y. Then you can, out of them, you can build a formal power series x of z like this, okay? And then let's plug this here in HM or in HGN. Let's plug it here. So in place of xi's, let's write x of zi. So we introduce new variables in place of variables x1 and so on xn. We introduce new variables z1 and so on zn, which are related by this change of variables, which coincides with an ACEH formula for their spectral curve. Okay? Then it turns out that this makes sense. So you can plug it as a formal series here, and you will a priori, you will obtain an even more complicated formal power series in z variables after you plug this expression for x in terms of z variables here. But it turns out that in full generality, for arbitrary formal power series, without making any restrictions on their coefficients, we can prove the following theorem. So this is already available on arXiv via this number, which I gave in the slide with the title. So what is the theorem? The theorem is as follows. So once you plug those x guys in your expressions for HGN, you can say that HGN can be represented as a sum of this form. Well, we call it stable GNN, namely not equal to 0, 1, or 0, 2. For 0, 1, and 0, 2, there are specific formulas as well. Just for brevity, I don't list them here. But for a general case, you have formula of this sort, where, so first of all, here, the sum will be finite over J's. And who are all the ingredients here? D is this differential operator, x d or dx, which in z variables, it looks like this, 1 over q, z d or dz, where q is given explicitly as a formal power series, like that, extracted from series y psi. Then p, who are those p, j1, and so on, jn, they are polynomials in 3 types of expressions. So this is one type. The other type is just kth derivative of series psi. And another type is the derivative with respect to log z, so z over dz to the power k of the series y. And Cgn is just some constant for which we give an explicit formula. So what does it all mean? It means that, well, I would say miraculously, this whole complicated formal power series for HGN, this one, after you plug for x in place of x this formal power series, this expression, it becomes much simpler. It becomes a finite combination of just derivatives of psi and y, of the original series psi and y. And we can prove this for, like I said, for arbitrary power series psi and y. So this is the first result. So for now, well, it can be actually we actually give explicit formulas for p. So you can, well, from this form of the theorem, like I presented here, it's not clear how to explicitly construct HGN using our approach. But in fact, we actually give an explicit formula for p, and it's computationally efficient. So you can plug our formula in Mathematica and compute HGNs as finite expressions in effective way, explicitly. I will, and a bit later, I will give explicit formula for this p. But for now, let's know that so for instance, if we know that y prime and psi prime derivatives, formal derivatives of y and psi, if they are rational functions themselves, then this theorem immediately says that HGN is a rational function in Z1 and so on Zn. And this corollary is very important for topological recursion. In a few slides, I will introduce topological recursion and I will say why it's important. Are there any questions regarding the statement of this theorem? Okay. So what else I wanted to comment here? Yeah, so do know that this is the main result of our first paper, which is already on archive. And in the second paper, using this result of the first paper, we proceed to topological recursion. So here, let me at this point, let me note that in a way, well, this is even in some ways more interesting than topological recursion, because you can think of topological recursion. Well, it's a little bit shallow at this point because I haven't talked about the definition of topological recursion, but for those who know it, so topological recursion can be thought of as a way to construct endpoint functions, but it's actually a rather inconvenient way to do this, because Oh, well, we will see it when we discuss it in detail, but it's hard to compute the endpoint functions explicitly on computer, for instance, for any given specific problem, because there, so you need to for instance, find all the some zeros of complicated algebraic expressions, and it's not feasible for all but very simplest examples. And so topological recursion as a practical tool of computing endpoint functions, it's not very useful because it's hard to use it. And our formula here also gives you the endpoint functions. No, well, I mean, in not such a full generality as topological recursion, but in almost this generality. I will comment on this later. But it's also practical, as opposed to topological recursion. Using our formula from this theorem, you can explicitly, for any given example, you can just plug it into Mathematica and it will produce you quickly the needed HGNs.
Petr, may I ask a question?
Yes.
So does the number of terms in your formula depend on psi and y? So you are saying that it's finite, but
no, it doesn't. It doesn't.
It does not. Mm-hmm.
No, it's yeah, the number of terms. It's finite, but it's like I said, you will see it in the explicit formula. So there is an explicit formula, and yeah.
So it means that you can somehow take your j's to be smaller than something. Is that right?
Yes. So you will see, like I said, so you will see that in the explicit formula.
Okay. Sorry. The number of summons depends on G and N, but not on psi and y.
Yes, it does depend on G and N, of course. So this for fixed HGN. So this is the expression, and the number of summons. It does. It's not some fixed constant. It does depend on G and N, but not on y and psi. Yes. So this will be after you write down all this. So you can write this formula without specifying y and psi. There will be finite number of terms, and it's completely general for all possible psi and y's. Okay. All right. So here I'm giving precisely this.
Yes. Sorry, maybe before passing to the H expansion and recursion, can you just give a hint where from this comes, or you just take some, some change of variables, use it, and so how to understand all that? What's going on?
Well, yes. So let me. So on the next slide, I've written down the explicit form of this formula, and let me explain that, and after that I will comment on how does this appear. Okay.
Okay, I'm sorry, may I ask one more question? So if you are saying that the number of terms does not depend on psi and y,
yes,
and then you also explained that if both are polynomials, then this was known, yes, before. So why can't you just take the limit?
No, this formula, it was not known. What was known was that it satisfies. What was known was that when psi and y were polynomials, then HGN they satisfy topological recursion. Mm-hmm. Formula like this one was not known.
But am I right that it's enough to prove your formula for polynomial?
Sorry, could you repeat this once again?
So am I right that it's enough to prove your formula for polynomials y and psi?
So you mean that the fact that they do satisfy topological recursion, it is enough to prove our formula?
Mm-hmm. Okay.
Well, no. So this was your question, right?
So my question was that can you truncate the formula? So is it enough to prove for polynomial psi and y?
Is it enough to prove? You mean that suppose we somehow prove this for polynomial y and psi, will this be enough to see that this holds in general? Just one moment. Yeah, I'm not sure. So
okay.
No, in fact, I mean, we don't know, like I said, so we don't know. So the only way which we know of how to prove this in general, in fact, it works for also general formal theorists. So yeah, we get the this form of the answer, the general form of the answer right away.
Okay, thank you.
By the way, in the polynomial case, if you apply topological recursion relation, then the number of summons in the process of application of this procedure does depend on psi and y. And if you have complicated psi and y, polynomial, but complicated psi and y, that you have bigger and bigger number of summons depending on the degree of these polynomials.
Yeah, so thanks for the comment. So yes, this is this fits into what I mentioned, that topological recursion is a much worse way of computing this endpoint function in practice. So here the expressions they do not depend on psi and y, and they're finite, and it's simple to compute them, as opposed to what you get in topological regression. So in a way, what I wanted to say here is that in a way this result is, in some sense, it's more interesting than the topological recursion itself, because in practical approaches, it also gives you a way to compute endpoint functions, but it's a better way. So in that way, it's interesting. Why the topological recursion? Well, I mean, why do we even go after that to topological recursion? Well, I mean, it's interesting because topological recursion, it's a bit more general theory, so it is also valid for some examples which do not fit, or at least we don't know how to fit them into this picture. But in fact, there are not very many of those examples. But in any case, so this topological recursion, it's a more general, more general theory with some connections to other fields of science like matrix models and so on. So from the point of view of connecting this to other known fields and results, topological recursion is interesting, but as a practical tool, this is more interesting. In fact. Okay, let me say a few words about the explicit formula here. So here, let me at this point already go to the H-deformed case. So consider in place of psi and y, let's consider what we call psi hat and y hat, which are from now on formal power series, not just in z and y, but in h bar squared as well, like here. So here at this point, they can be arbitrary power series. And then let's define psi without hat and y without hat by putting h to 0. Okay. So then it turns out that the theorem works if you consider the change of variables to be the same. Here you do not put psi and y hat. Here it's in the change of variables you use psi and y without hats. This makes sense from the point of view of connection to topological recursion, because spectral curves, it should not depend on h bar. So here you use the regular psi and y without hats in the change of variables, but then explicitly the theorem can be formulated like this. So let me explain what happens here. It's a little bit complicated, but let me spend a few minutes on explaining how this works. So for simplicity, I will present the general theorem not for HGN themselves, but for what we call WGN, which are derivatives with respect to this capital D differential operator of HGN, defined explicitly like that. And then in fact, once we discuss what happens when we pass to topological recursion, those guys, the WGNs, they are precisely the guys which we are interested in, because topological recursion, it is formulated in basically in terms of these WGNs, not in terms of the HGNs themselves. So for passing to topological recursion, we don't even need the explicit formula for HGN, but in our paper we do have it. So here I formulated it in this more general form without specifying who are the P's. In fact, we can do this. So in this next slide, I give explicit formulas for P's when you consider not the HGN itself, but D1 and so on DN HGN. But for HGN, we can also give explicit formulas for P's. It's a little bit more complicated, but we can do this. In this talk, I will not do this because it's not interesting from the point of view of proceeding to topological recursion. And the formulas look a little bit more bulky, but it is possible. And this is what we do in the paper. And we also supply explicit formula for this constant CGN as well. So this is all present in the text. But for now, let's consider just this case, which is a little simpler. And it turns out, so our theorem says in fact that this can be represented as follows. So you take here, so who is these guys? Consider WKLs as the weights. Yeah, sorry, I haven't introduced, I think, the curly S. I think I forgot about it. So this curly S, let me write it like that. So curly S is equal to X, curly S of, let's say Z, or U, curly S of U is equal to X of U over 2 minus X of minus U over 2 divided by U. So this is the definition of curly S. And this W, it's considered to be a weight. So we consider here some overall connected simple graphs on n labeled vertices. So simple graphs meaning that we don't have double edges and we do not have loops. Edges returning to the same vertex. So this is a finite sum over gamma, just all connected simple graphs on n vertices. Then consider such a graph, and on each edge, so this E gamma is the set of edges of gamma. On each edge, you put a weight like this, and consider the product of all such weights. And after that, you apply a complicated operator of this form. So where UI is an operator acting on function f like that. So, so how do we even, well, I mean, so this looks to be a quite complicated formula. Let me say a few words on its meaning, so how to apply it, and a few words on how we obtained it. So, so first of all, a few words on how do you apply it in practice. Well, you can see that, I mean, I advertised our formula to be finite. Well, and here you can see, for instance, that this is an infinite sum over J and R. Why the resulting expression, why will it be finite? Well, after you take the coefficient in front of, so here this H bar to the power 2G minus 2 plus N in square brackets, it corresponds to taking the coefficient. So you consider this whole guy, which you plug here, and you consider it as a series in H bar, and you take the coefficient in front of H bar to this power. And it's actually somewhat easy to see from this formula that after you take this coefficient in for fixed power of H bar, this whole thing becomes finite. Because here, with the rising J and R, it turns out that the power of H bar, it necessarily rises. So for fixed power of H bar, only a finite number of terms here will contribute, and it's even possible to say how many of them. It just won't be very pretty because it will, so you need to use the explicit structure of functions curly S, which are functions like that. So then, so this is this command that this is in fact, this will be in fact a finite expression. And let's see why, as I advertised, why will it be a finite rational expression in expressions like this and the derivatives of psi and y? Well, you can actually see this here in this formula because psi, more precisely in terms of psi hat and y hat. So psi enters here, only here, and in fact, looking at this formula, it's easy to see that there will. It's actually better to look at this formula. Only derivatives of psi will appear because here the part without derivatives, it will get cancelled, and only the derivatives starting from the first derivative, they will enter in the final expression, and the same regarding y. So you remember that this d was a differential operator, x over dx, or in terms of z, this qi times dy is zi d over dzi. Now, so how do we obtain this? Well, I haven't even, at this point, I haven't even attempted to write down the steps of how we do this in the slides because this won't really fit in one talk. But let me say a few words on how this can be obtained. Well, basically, you start from the definition. So you start with the with this definition, with the derivatives of f, and then you write it in terms of correlators. So you can write this in fermionic way or in bosonic way as correlators, and with the help of writing it as correlators, you know this will be a correlator of some operators, either in bosonic or in fermionic form, and then you can commute these operators, and well, you will obtain some further expressions which are not much simpler than the original generating function, but then we need to see that. We need to see how to arrive at this formula. So there are some k lemmata which are given in our paper, which turn out to work in this case, where it turns out that once we pass from connected from disconnected numbers. So this whole statement, remember that this whole statement it's about connected HGNs. So once you start with disconnected numbers and you write them as correlators of operators, and once you go to the connected numbers, basically all your problems get canceled. Let me finish outlining the sketch of the idea of how we go to topological recursion, and after that, if there is still some time, I will write formulas for in terms of correlators and give more details on how we obtain formulas like this. Okay. So I mean, I understand that this formula looks rather bulky and it's hard to understand it right away, but so still, so are there any questions at this point? All right. Now let me, I guess I will erase this again. Let me formulate the spectral curve topological recursion. Remind the definition of spectral curve topological recursion. Well, I mean, recall that the spectral curve topological recursion, it originally appeared in matrix models. In matrix models, you can consider for a given matrix model what's called the spectral curve, and on this spectral curve you can consider resolvents, and there are some recursive formulas which relate those resolvents between themselves. Then Eynard and Arantin, they generalize this to an arbitrary case when you don't have any matrix model. You just start with any algebraic curve. Well, usually in applications, this algebraic curve is just a Riemann sphere, but there are also known applications of curves of higher genus, which correspond to some interesting examples. But for now, let's think of it as of the Riemann sphere. And you have two meromorphic functions x and y. And in fact, it's not required that, so you can generalize this, lifting the requirement of them being meromorphic. In some interesting examples, they can be given, there can be logarithm centering. This can be done. You can formulate it in a bit more general situation. But then you also have what's called the Bergman kernel B, which is for the sphere. B is given by, let me write it. So for the sphere, B is given by dz1 dz2 over z1 minus z2 squared. And you construct recursively what's called the endpoint functions or n differentials on this spectral curve, which are called omega gn. And you start with the initial data omega 01, omega 02, given by y and x and b. And after that, you use the following recursive formula here. C's, Cj's, zeros of dx. So this again, it's some, at first glance, it's some monstrous formula. But it has some nice geometrical interpretation where you can think about this G as some, well, fake genus of something, and here these terms here, this part corresponds to, say, pinching the handle, and this corresponds to pinching the surface in a way that it separates into two. Well, this is just some geometrical mnemonic way of understanding it, but so this formula, it's known for many examples, for Hurwitz-type problems, for Gromov-Witten theories, for homological, semi-simple homological field theories in general, and volumes of hyperbolic volumes of moduli spaces of curves. Other examples. This is already quite well studied in many particular cases. But let's point out that, I mean, I mentioned that this is not a very practical formula. So for instance, look here that this formula, so it's local. You're only interested in the behavior of all those functions near points Cj, which are zeros of dx. And even if your x is some polynomial, or I mean, it's some simple expression where, well, the equation will be algebraic on those zeros of dx. Still, in most examples, this will be, even in the simplest case when it's algebraic, it's an algebraic equation of usually some high degree. And in order to use this formula, you need to find zeros of dx. So you need to solve this algebraic equation of some high degree, which is completely impractical for high degrees, right? You cannot do this in general, and this whole recursive formula, you can, in practice, apply it only if you know the CJs and you study the behavior of, local behavior of all those functions near the CJs. So you cannot avoid this in this formulation of topological recursion. You cannot avoid hard algebraic, for instance, algebraic equations of high degrees. So this cannot be plugged into computer to easily produce you answers for omega Gn. It's an interesting property which can be proved to be satisfied for some cases, but as a practical formula, it's not a very good one. All right. So now, yeah, let's again erase this.
Sorry,
Yes.
may I ask a question? Isn't it true that the right-hand side of this formula can be in some way expressed as a symmetric function of this CJs?
Symmetric function of Zi's, you mean?
No, I'm asking about CJs. So is it necessary to find OCJs, or there are possibly some tricks which can express the sum or zeros in terms of initial function?
Well, yeah. No, I mean, at least the ways I know of how to compute this in practice, well, in general, they do involve finding the CJs. So at least I don't remember whether it could be possible to do this without explicitly finding CJs. If you want to explicitly construct omega Gns, at least. Yeah.
Okay.
All right. So now, in order to relate this to the first part, to our result on rationality of the endpoint functions, let's give another formulation of topological recursion, which is even less practical. So it's a formulation in terms of loop equations. Basically, what is this formulation? So it's written down in several papers, Barrow-Eynard-Harnad and Barrow-Chandran. Consider WGNs, which you obtain when you take the cut out the dx part of omega gn, and yeah. So sorry, I jumped to a bit different notation. So here PIs are the guys which were called CJs here. So they are the zeros of dx, and it turns out, so it can be proved that topological recursion holds if the functions WGN of Z, they satisfy three properties. So one is the so-called projection property, which says that for stable GNN, WGNs basically they should be homomorphic at the.
Petr, it's just opposite.
Oh, yes, sorry.
It's has false at PIs and homomorphic
I'm sorry.
in the complement.
I'm sorry. This, I'm sorry. This is. I think something got mixed in. Yeah, this is a misprint. So this is WGNs should have poles poles at PIs, simple poles at PIs, and no other poles.
What do you mean simple?
Oh, sorry. Poles at PIs and no other poles. Yes, and no other poles. So WGN should have. Yes, sorry, this was in the text file. This probably came from the second property, which is the linear loop equation. So the WGNs they have the first statement, the projection property is that they have poles at PIs. So basically, WGN they should belong to the space which we call Xi. Let me explain it. This is the space formed by 1 over Z minus PI, and here you can apply a number of D's, di to some power k, and so this is the linear span of functions of this sort. Sorry, let me write it better. So to understand what I mean by this condition, so consider space Xn, and then it should be the linear span of functions product from 1 y to 1 to n, a product of sorry. So di to some power ki applied to 1 over zi minus pj, and consider linear span of all these guys, this will be some space of functions on the curve, and the projection property states that this WGN should belong to this space. So basically, it has poles at points Pj and no other poles. All right. So then the other two properties. Let me erase this. The other two properties are the linear loop equation and the quadratic loop equation. The linear loop equation states that, well, at this point we consider that that the zeros of dx, they should be simple, and this sigma I, it's the involution near this ith zero of dx in the covering x of z. Then the linear loop equation states that this sum should be holomorphic near at point pi for all points pi. And the quadratic loop equation, it says that this quadratic combination of w's, which should remind you this part of the formula for the recursive formula for the spectral curve topological recursion. So this should also be holomorphic near in Z near pi. So this is actually not precisely the same sum as here, because here this contains prime. Prime here, I didn't mention it, but prime here means that we do not, we discard terms in this sum where we have 0, 1 here. When one of the omegas, it becomes omega 0, 1. And in this sum over here, we take all possible terms. So there could be 0, 1 w's. So this is the quadratic loop equations. And now let me comment on the so how is this related to this Hurwitz-type problems, and which we considered in the first part, and what does our theorem mean in application to this topological recursion. So let me repeat that this is an alternative formulation. So sorry for this mistake here with the projection property. So this alternative formulation, like I said, so it can be proved that that the fact that WGN satisfy the three properties, it is equivalent to this original formulation, recursive formulation of topological recursion, but it's even less practical because, I mean, how do you use those three properties if you want to explicitly find the endpoint functions? Well, I mean, you can. Basically, what you do is you recover out of this condition, this last condition, you recover the highest order W and express it in terms of the rest of them. You arrive basically at this formula. But anyway, so in terms of relating this to the original part, to the first part of originality of generalized Hurwitz partition functions, well, this is more convenient to prove the projection property, linear loop equation, and quadratic loop equation. And let me now state so what we know. So here it's again the formulation, our general formula for the WGNs. And first, let me say what do we get for the projection property. So for the projection property, it's actually the most restrictive one out of all three properties. So the projection property, it turns out that you can we can prove using our formula, so this formula, using this formula, we can prove if we pose additional requirements on psi and y, we can prove that the projection property holds. For now, we can do this for two families. So the first family is like this. The first line of this table, the first row in this table, and the second line is the second row in this table. So what does this table mean? It turns out that if you use psi, if you take psi and some psi and y, not depending on h bar, so just look at some psi of y and y of z, like at the beginning, which do not further depend on h bar themselves. And then you take a spectral curve given by this formula, like Alexandrov-Chapuy-Eynard-Harnad do. So you use, for your y of z, you use just y, and for x of z, you use this guy. Then you can run topological recursion as defined here. You can run topological recursion on that curve, and you will obtain some endpoint functions, Wgen. It turns out that, in fact, if you do this for a Hurwitz-type problem like that, if you consider a spectral curve like that and run it when you know that topological, run it for a spectral curve of that form, it turns out that what it gives you, Wgens, it actually gives you Wgens for h bar deformed case, for the h bar deformed case. So for instance, if you consider psi to be of this form, for instance, here p and all the p and r's are polynomials. So here alpha is a constant, and all the pi's and ri's, they are polynomials. So consider this. Let's look at, for instance, at the first line. When all the pi's are polynomials and ri's are also polynomials. It turns out that you need actually to consider an h bar deformed psi of this form. So here, if you start with, for instance, if you do not have this logarithm part, which you might not have if this polynomial P3 is just a constant and P4 is also constant. So suppose this P3 or P4 is 1, then you do not have this logarithm and you have just a rational function here. It turns out that in order to get for your endpoint functions, which topological recursion gives you, in order for them to coincide with the endpoint functions of the original partition function, which we defined originally, you need to, instead of taking this psi, you need to take psi hat instead, which will depend on h bar and which is given by this formula. And in the second family, where psi is equal to y and times a constant, and y can be again a rational function plus a logarithm of a rational function, you need to consider a unique deformation like this. In fact, this precisely corresponds to what we get for, let's go back to what we get for the R spin numbers, R spin Hurwitz numbers, and the extended Ooguri-Vafa. So these formulas here, they are precisely of this sort. So this, if you consider what psi of y do you have? So here psi of y, once you plug h bar to 0, what is left here is just y to the power r. And once you plug h bar to 0 over here, what you get here is a logarithm of the ratio of two linear functions in Z, in this case. So this is precisely, these two examples, they are precisely examples of when in that table we need to introduce psi hat depending on h bar. So what we can prove that projection property is actually satisfied, at least in those two families. And there is, like I said, so there is a unique reconstruction of a psi hat from psi and y in those cases, such that the projection property is satisfied. So how do we prove this? We look at this formula here, and what do we do? So our theorem here, it states that this is some rational function in Z, in fact. So here you can see that those examples are, in fact, correspond to the cases when psi prime and y prime are rational. So this will be a rational function in Z. So what you need in order to see that this belongs to this space, Xi, which I defined a little bit earlier. So you need to prove that there are no other poles than the zeros of dx. Zeros of dx are, in fact, will coincide with the zeros of q here. So we see that there are some poles at the zeros of dx in this q, which also enters this d here. But we need to see that there are no other poles. So this, and also we need to see that the top degree, so the degree, asymptotic degree of the expression for this WGN when Z goes to infinity, we need to see that it is bounded from above by some specific number in order to see that it belongs to that space Xi. We can do this by analyzing this formula for those particular cases, and by carefully analyzing it, we can see that this in fact holds. So this projection property is in fact the most restrictive one. Then the statement which I also have on this slide is that in fact if you consider here just arbitrary series psi and y, now if you want to go to topological recursion, you need to say that these series they correspond to some spectral curve so that they have a non-zero radius of convergence. So the only well, I mean, our theorem on rationality, it holds for arbitrary formal series, but if you want to go to topological recursion, you need to put some restrictions. So first of all, you need to say that in order to get linear loop equation and quadratic loop equation, you need to say that these guys, they have a non-zero radius of convergence. Then you can extend them to the whole spectral curve. And after you do this, linear loop equation you get immediately after you study this expression for WGN. It's easy to see that the linear loop equation, which is this condition, it immediately holds. And for quadratic loop equations, you need to again look at this expression, and basically what you do is you can consider this whole quadratic expression, which stays in quadratic loop equation, and you show that for this expression, you can get actually a similar formula to the one which we have here for just W. We can get an explicit formula for that, and from there we see that the quadratic loop equation is satisfied as well. So yeah, how much time do I still have?
Not too much. And I think that people are already tired, so maybe you try to concentrate on some statements.
All right, so at least, I mean, speaking of general statements, I've already given them. So we have our main theorem, which is basically this one, where we give explicit expression, main theorem of the first part, where we give explicit expression for WGN. And then we can prove that it satisfies topological recursion for two quite large families of psi and y. And in fact, those two families, they cover all already known examples of Hurwitz-type problems where there exists a proof of topological recursion. So you might think that this is a bit restrictive, representing this psi and y as some rational expressions plus logarithms of rational expressions. You can think that this is restrictive, but in fact, it covers all known cases when there is known topological recursion for Hurwitz-type problems and more. So this is a more general statement. So maybe this is our current state of progress. So those two families. Maybe our formula actually allows to prove this even for some more general cases, but we don't know yet precisely. So these are the statements, and like I said, so regarding the proofs of these statements, the detailed proofs would take more time. So, and yeah, so out of any of this, well, there are several parts. So the proof of the original statement, then the proof of projection property, and the proof of loop equations. So there are basically three separate parts which have their own proofs. So that will, any of those parts will probably take at least an hour to properly explain with all details. Yeah. So are there any questions at this point? So I can comment on, if there is some more time, I can comment on how to prove on ideas of proofs or of any of those parts, or I can comment on some of the applications like the Zwonkins conjecture. So what would be better to do? Or maybe there are some other questions. So are there questions at this point? No, okay, so let me maybe formulate this Zwonkins conjecture, which will be, so is there like 5 more minutes to formulate Zwonkins conjecture, or everybody?
Yeah, I think it's good. It's a good thing you stressed it. So 5 more minutes for Zwonkins conjecture. Yeah.
Okay. So what is the Zwonkins conjecture? It's basically like this. So the sorry. Yeah. So the here on the left hand side, these guys are the R-spin Hurwitz numbers, which in a moment I will explain who they are. And on the right hand side we have, so this is what's called an ELSV type formula. So on the right hand side here, these are the some integrals over the moduli space of algebraic curves of CGNs. They are what's called the Kyoto classes. So they depend on some of those parameters, and psi are the psi classes. Then the so this right hand side is this rather complicated integral over moduli space of curves. And on the left hand side, so who are these R-spin numbers? Sorry, I think I moved this slide a little bit further. I'm sorry. So this, yeah, here are the R-spin Hurwitz numbers. R-spin Hurwitz numbers, they come from completed cycles. So you consider well, shifted symmetric functions, and you can build completed cycles related to them, which are given in this form for the first 5 ones. And then we can consider a Hurwitz-type problem. Recall that originally for simple Hurwitz numbers, you studied factorizations of a permutation as a product of transpositions. And for R-spin Hurwitz numbers, you consider factorization of some permutation of cyclic type mu as a product of permutations which are no longer just transpositions, but so they should enter the completed cycle. So for instance, here, so the simple Hurwitz numbers you get for R equal to 1. So you consider R plus 1 completed cycle. In this case, it will be C2, which is just C2. C2 corresponds to 2 corresponds to transpositions. So this 2 corresponds to cyclic type of the permutations sigma I, and these sigma i's, they should enter in general, for general R, they should enter the CR plus 1 completed cycle. So for instance, for C5, you should see not only transpositions, but permutations of type 2 or 3. And so you take a factorization of this sort and assign to it a weight, which is the product of all the coefficients for all sigma i's, where the coefficients are the numbers which enter the here the completed cycles, and then adding all those weights. So if you take the sum of all the weights, you get the connected R-spin Hurwitz number here. Well, so this is what stays on the right in Zvonkhin's conjecture here on the left. So here you get you take the those Hurwitz numbers arising from completed cycles. So they originally, I think they were considered by Kunkov and Pantaripanda in, let me see, I have this slide here. Yes, so they considered them in relation to relative Gromov-Witten theory of CP1, and they proved that in the relative Gromov-Witten theory, you have a formula like this. So this is a specific case of Kunkov and Pantaripanda formula. their formula is more general, but restricted to just some simple part of it. You get this, where on the left is the R-spin Hurwitz numbers like I defined them, and on the right are the relative ground-width invariants. So they started those R-spin Hurwitz numbers in application to relative ground-width invariance, and then Zvonkhin conjectured, like we see here. So he conjectured that in fact they can be expressed as over and in terms of integrals over just the original moduli space of curves, compactified the Lin-Mumford moduli space of curves of Kyoto classes. So Kyoto classes, they are related to the spin structure on curves. So you take some linear bundles and take the out roots of those bundles, and out of that you construct, using Chern classes, you construct the Kyoto classes. So they are some Chern classes of Rth root bundles, and they have some interesting meaning. So Kyoto proved some interesting results regarding them. But so Zvonkhin's conjecture was that this holds, and in fact so this was proved last year originally by us in a different way, which is somewhat more complicated. But now we can, using the results which I explained today, this can be proved. This can be seen as a quite easy corollary. So basically, this Zvonkhin's conjecture, it follows from the fact that the left-hand side satisfies topological recursion, because the right-hand side is a homological field theory, and there was an earlier paper. So in our, let me write it here. So in this paper, in our paper with Arantan, Chadran, and Spitz from 2012, we proved that basically arbitrary semi-simple homological field theory corresponds can be reproduced by topological recursion, and this holds for this theory, for this homological field theory. Just apply the results of this paper. Well, there are some subtleties there, but it can be done quite easily. And then and in fact, it turns out that it is reproduced by topological recursion on the same spectral curve which you get for the R-spin case in the Hurwitz case. And then if they are both reproduced by the same topological recursion, then they should be equal. So this you get as a simple corollary from our theorem.
Thank you. Any questions?
So let's go back. Yeah.
No questions at all?
I wanted to ask about involution in topological recursion.
Yes. Mm-hmm.
So it's a part of definition. Yes, sigma is a part of definition.
Yeah, sigma. Let's go back. So sigma is a part of definition. So you say we assume that in the simplest cases. So if you want to formulate it like this, we assume that dx has simple zeros, and sigma I is the involution simple zeros Ci near Ci.
Involution. Sorry, what involution?
What involution? So we have, if you consider X as, so here you have your sigma, and here you have CP1, here the map X. So if you have a simple zero of dx, this corresponds to, so this will be a ramified covering, and this will look like this. So if this point is Ci, so the involution sigma I, so here it's the map X. This is sigma. So the sigma is a map from sigma, X is a map from sigma to CP1. Looks like it defines for you a ramified covering, and the involution. And if Ci is a simple zero of dx, then you have two sheets intersecting at this point, and sigma I is the involution here between those two sheets. So it's defined by the condition X of sigma I of Z is equal to X of Z, and also that for Z tends to Ci, sigma I of Z also tends to Ci.
Now it's invisible what you written.
Oh, sorry, it's invisible. Does it?
Yes, when you drawn a curve and ramification point, it was okay, but now the last formula was invisible.
Okay, let me write it over here. So, sorry, over here, is it visible over here? So Z, when Z tends to Ci, sigma I of Z tends to also Ci. So basically like here. So if this is the intersection of two sheets, sigma I interchanges the 2 points with the same X on those two sheets which intersect at Ci.
So we require zeros of dx to be a stable point of this involution, yeah?
Yes, yes.
Fixed point.
So
and
sigma I is defined. Sigma I is defined. It's locally defined near Ci. We only need it locally because, as you can see, yeah, sorry, here I think should be A, if I write it like that. So sigma, this index sigma A should be the same as the index of C here. Sorry.
And from this requirement, we see that we got Po in denominator, and we have to point to residue. Yes.
Yes.
So okay. And for example, if you take curve to be hyperelliptic, this is the usual involution. Yes.
If it's well, this this depends on what your X is. So,
for example, let y squared be polynomial of X.
So you mean if the curve is y squared is p of x, like that? So if Z, yeah, if we say that, yeah, right, yeah.
So we just send the y to minus y, yes?
Yes.
But in most cases that was discussed in this lecture, the curve was rational. But
yeah, so like I said here,
cases,
in most cases, yeah.
some extension of this stuff.
Yes.
And in rational case, but it is still can be defined globally, and it is still.
What can be defined globally? What can be defined globally?
Involution.
The involution, no, it can only be defined locally because I mean, you can have some. I mean, this X, it's it defines for you ramified covering. So once you can have some other ramifications over there, and I mean, it doesn't make sense to interchange sheets when you're far from this point. So, and also, you don't need this because in this, I mean, after I corrected it here, as you can see, oh, sorry, this A here, A from 1. after I corrected here, you see that you only use sigma I near the point CA because sigma A near the point CA because you take the residue at CA.
But if we can define it in a unique way locally, how can we define? Because
Sorry?
can we define it locally in a unique way?
Sigma I?
Yes.
We can define it locally in a unique way.
By what condition?
I mean, by those two conditions, so that x of sigma of z should be equal to x of z,
Yes.
and that for z tending to Ci, sigma I of z should also tend to Ci.
But why can't add any series which vanishing at z, and this will not change? It seems that it will not change.
No, as you can see from this picture, the x coordinate near this point, so this x defines a ramified covering over CP1, right? So the if you fix your x coordinate, so you have only discrete freedom. You need to fix what sheet then you choose, and
sorry. Yes, I see. Sorry. Yes.
so then sigma, if you are near the point Ci, then in some small neighborhood, then you can only be on those two sheets which intersect there, and then sigma should keep you in on those two sheets.
Sorry, I misunderstood this condition.
Okay, so I think that after 2 hours, everybody is very tired. So we just maybe thank Petr for informative talk. So
Thanks
to everybody.
Thank you.
Thank you.
Thank you.
Паша, вы можете там что-то остановить, да?
Не, я разве что стрим на ютубе могу прибить. Еще закрыть не могу.
Ну хорошо.
Ну, в общем, как бы с подробностями доказательств это невозможно один доклад вместить, но...
Невозможно.
В общем, если у кого-нибудь будет желание, то я могу в любой момент, естественно, рассказать любые части из подробностей отдельных доказательств.
Ладно, спасибо.